Today, new data on the interstellar object 3I Atlas was released from the Hubble and Webb Space Telescopes in two papers. The Hubble Space Telescope report includes a successful detection of the music nucleus of 3 Atlas based on post-perihelion data from December 2025 until January 2026. When the image finally arrived, many believed the mystery of 3 Atlas was about to end. 4 months astronomers waited for James Webb to photograph the object's true nucleus, hoping a clear picture would settle debates about its nature. Instead, the image did the opposite. The nucleus appeared larger than expected. Its chemistry refused to follow known patterns, and its behavior no longer matched what scientists associate with natural comets. What was meant to close the case only widened it. If size, composition, and motion all point in different directions, the real question becomes unavoidable. If 3 Atlas does not act like a comet, then what exactly are we observing as it moves through our solar system? For a long time, scientists could not directly see the true nucleus of 3 Atlas. And this limitation shaped almost every early assumption about the object. From Earth-based telescopes, 3 Atlas appeared wrapped in a bright cloud of gas and dust known as ʻOumuamua, which reflected sunlight and masked whatever solid body lay beneath. As a result, astronomers were forced to rely on indirect brightness models where size was estimated from light output rather than direct observation. And those models often favored smaller, lighter objects. This uncertainty was not a technical failure, but a physical one. Before perihelion, the intense activity of 3 Atlas made it nearly impossible to separate the glow of the surrounding material from the nucleus itself. Even powerful observatories like Hubble could only infer the core's presence through subtle changes in light, leaving room for wide disagreement across the scientific community. Some researchers argued for a compact body, while others warned that hidden mass could be buried beneath the active surface. James Webb changed that situation because it was designed to look where others could not. As an infrared telescope operating far from Earth's heat web can detect faint thermal signals that visible light instruments often miss. After 3 Atlas passed perihelion and its activity dropped, the surrounding coma thinned enough for Webb to isolate the nucleus with far greater clarity. For the first time, the object was no longer a glowing blur, but a defined body with measurable properties. The difference between observing a coma and observing a nucleus is critical. A coma reflects current activity, which can rise or fall quickly, while the nucleus represents the object's true structure and mass. By focusing on post-perihelion data, Webb allowed scientists to stop guessing and start measuring, replacing assumptions with numbers that could be tested and debated. This shift marked a turning point because every major theory about 3 Atlas depended on how big and heavy it actually was. When the measurements emerged, they did more than refine earlier estimates. They challenged the foundation of many explanations that had seemed reasonable only months before. Models built around a small nucleus suddenly looked fragile, and ideas about how the object formed or evolved had to be reconsidered. The image did not bring comfort or closure, but it provided something more important, which was a solid reference point that could not be ignored. Yet the most striking outcome was not simply that the nucleus had been revealed. It was that clarity made the mystery sharper rather than smaller. Once the numbers were in place, scientists were forced to confront a deeper issue. If the nucleus was now visible and larger than expected, how could its behavior still resemble that of something much lighter? That question leads directly to the next problem, because size alone was only the beginning of what no longer added up. The moment the new size estimate was released, the entire story of 3 Atlas had to be reconsidered. Based on post-perihelion observations, scientists now placed the diameter of the nucleus at around 2.6 kilometers, with the possibility that it reaches close to 3 kilometers. At first glance, that difference may sound small, but in physical terms it changes almost everything about how the object should behave. For months, most earlier models assumed a nucleus closer to 1 kilometer in diameter. Those assumptions shaped expectations about mass, structure, and even how strongly the object could react to forces near the sun. What many people miss is that mass does not grow in a straight line with size. When diameter increases, mass rises much faster because volume scales with the cube of that diameter. In simple terms, a body that is roughly 3 times wider can be more than 20 times heavier. This is why the new estimate caused such a strong reaction across the scientific community. A nucleus measuring nearly 3 kilometers across is not just slightly larger than expected. It represents an object that carries far more material, far more inertia, and far more resistance to change than previous models allowed. Ideas that worked for a light object suddenly became unstable when applied to something this massive. The comparison with earlier interstellar visitors makes this difference even clearer. Objects like ʻOumuamua and 2I/Borisov were much smaller, and their behavior fit more comfortably within existing comet models. 3I Atlas now appears to stand in a different category, not only because it is larger, but because its scale pushes it outside the range where simple assumptions still hold. This alone forces scientists to ask whether they're dealing with a familiar type of object or something that challenges the boundaries of current classifications. The immediate consequence of this size revision was the collapse of several explanations that once seemed reasonable. If 3 Atlas truly carries this much mass, then many of its observed behaviors become harder to justify using standard physics, music alone. Processes that can easily push around a small nucleus struggled to produce the same effects on a heavier one. The object did not change, but our understanding of it did, and that shift exposed cracks in earlier interpretations. More importantly, the new measurement removed the comfort of ambiguity. As long as the nucleus size was uncertain, theories could hide behind wide error ranges. Now, with a clearer picture, each hypothesis must confront the same hard numbers. Some ideas weaken under that pressure while others collapse entirely. This is why the size estimate was not just another data music point. It acted like a lever, lifting the surface of the mystery and revealing deeper problems underneath. Once scientists accepted how large 3 Atlas really is, they were forced to face a troubling mismatch. If the object is this heavy, then why does it move and react as if it were much lighter? That question leads directly into the next puzzle, because size alone cannot explain the strange behavior that followed. After 3 Atlas passed its closest point to the sun, many scientists expected its behavior to follow a familiar pattern. For most comets, peak activity fades quickly after perihelion as solar heating weakens and surface reactions slow down. At first glance, 3 Atlas seemed to do exactly that because its overall brightness dropped faster than it had risen before the encounter. This rapid dimming suggested that the object was settling down as if the most dramatic phase was already over. However, a closer look revealed that this calm was only partial. While the surface appeared less active, careful monitoring showed repeated pulses in brightness that did not fully disappear. These pulses were subtle but persistent, creating a rhythm that stood out against the general decline in activity. In many natural objects, such variations can be explained by rotation, since different surface areas come into sunlight over time. Yet in this case, the timing of the pulses did not line up cleanly with the estimated rotation period. This mismatch immediately raised questions. If rotation alone could not account for the changes, then some internal process had to be influencing what observers were seeing. The object behaved as if something beneath the surface was still responding to energy in a delayed or uneven way. Instead of a smooth shutdown, 3 Atlas showed signs of layer behavior, where some processes faded while others continued quietly. What made this even more unusual was the contrast between music, appearance, and activity. From a distance, the object looked calmer and more stable, which reinforced the idea that it was moving toward dormancy. Yet the ongoing pulsing hinted that the nucleus was not simply cooling down like a typical comet. This combination created an uncomfortable tension in the data because it suggested that surface observations alone were not telling the full story. Scientists began to consider whether the structure of 3 Atlas might be more complex than expected. If the nucleus contains regions with different compositions or densities, then energy could be released unevenly as the object cooled. Such internal differences could produce delayed reactions that appear as pulses long after the main heating phase has passed. This idea does not break known physics, but music stretches it, especially when combined with the newly revised size of the object. The key point is that post-perihelion behavior usually simplifies our understanding of comets. As activity decreases, interpretation becomes easier because fewer processes are active at the same time. With 3E Atlas, the opposite seemed to happen. The reduction in overall activity removed the music noise. But what remained was harder to explain, not easier. This is why the post-perihelion phase became so important. Music, instead of confirming expectations, it exposed signs that something inside the object was still at work. The calm surface masked a deeper complexity, and that complexity hinted that composition, not just size, might hold the next set of answers. If the structure is unusual, then the materials inside could be even more surprising. That leads to the next question, because once structure becomes uncertain, chemistry can no longer be taken for granted. Once the structure of 3E Atlas raised doubts, its chemistry deepened the mystery even further. Using infrared spectroscopy, James Webb examined the material released from the object after perihelion, and the results did not match what scientists expected from a typical comet. The chemical balance of the coma began to shift in unexpected ways. One of the first changes involved water and carbon dioxide. After perihelion, water vapor became more visible, while carbon dioxide showed a clear drop compared to earlier observations. At face value, this might seem normal since different materials react differently as solar heating fades. However, the earlier dominance of carbon dioxide, combined with the later rise of water, created an uneven pattern that was difficult to reconcile with standard comet models. The real shock came from the metals. Nickel continued to appear in unusually high amounts. Even as overall activity decreased, iron, which had been weak or absent before, began to show up more clearly. Yet the ratio between nickel and iron remained far outside the range seen in comets from our solar system. This imbalance matters because natural cometary material usually reflects the chemistry of the early solar environment, where nickel and iron appear in more predictable proportions. Here, that balance was broken. Scientists are careful not to jump to extreme conclusions, but the data forced uncomfortable comparisons. The only known environments where nickel appears so strongly without matching iron often involve high temperature or processed material. Natural explanations are still possible, but they require rare conditions that have not been observed in other comets. This does not prove anything artificial. It does place 3E Atlas in a chemical category of its own. What makes this even more striking is the timing. These chemical signals did not peak when the object was closest to the sun, where intense heating would normally drive the strongest reactions. Instead, some of the most unusual signatures became clearer after perihelion, when activity should have been fading. This reversal challenges the basic assumption that solar distance alone controls comet chemistry. Infrared data is especially powerful because it reveals what visible light cannot. By tracking how different molecules absorb and emit heat, Webb allows scientists to see not just what is present, but how materials are behaving at a molecular level. In the case of 3E Atlas, those behaviors pointed toward instability rather than equilibrium. The coma appeared to be evolving instead of simply shutting down. The key issue is not that one element looked strange. It is that multiple chemical clues move in different directions at the same time. Water increased, carbon dioxide declined, nickel stayed dominant, and iron appeared late. Taken together, these signals resist a single clean explanation and instead suggest a layered or unusual internal composition. At this stage, scientists can describe what they see, but they cannot yet explain why it happens this way. The chemistry of 3E Atlas does not neatly fit into the categories built from decades of studying solar system comets. That gap between observation and explanation is where the real tension lies. If composition already breaks expectations, then the next question becomes unavoidable. What happens when one of the most volatile molecules enters the picture and behaves in a way that defies every rule scientists rely on? That question leads directly to the most confusing chemical signal of all. Among all the chemical signals detected around 3 Atlas methane created the deepest confusion. In comet science, methane is known as a hypervolatile molecule, meaning it reacts quickly to heat and escapes early when an object approaches the sun. Because of this, scientists usually expect methane to first peak near perihelion and then fade as distance increases. That is not what happened here. During the early approach to the sun, when carbon dioxide and carbon monoxide were clearly present, methane was almost completely absent. This alone raised eyebrows, since methane requires less heat to activate than those molecules. If carbon-based gases were escaping, methane should have been impossible to miss. The real shock came later, after perihelion. As 3 Atlas moved farther away and overall activity decreased, methane began to appear, and not in small traces. Its production rate increased relative to water, reaching levels that made scientists stop and question their assumptions. Instead of fading with distance, methane became more visible, which directly contradicts the basic thermal behavior expected from such a volatile substance. Several natural explanations were proposed, but each one introduced new problems. One idea suggested that methane was depleted in the outer layers of the nucleus and only released after deeper material became exposed. At first, this seemed reasonable until researchers compared it with the behavior of carbon monoxide. Carbon monoxide is even more volatile than methane, yet it appeared early and did not vanish as the object evolved. If methane had been lost from the surface, carbon monoxide should have disappeared as well, but it did not. Another explanation focused on internal structure. If 3 Atlas contains pockets of material insulated from early heating, methane could remain trapped until later stages. This would require a highly unusual internal composition with layers that respond to heat in very different ways. While not impossible, such a structure has not been confirmed in any well-studied comet. What makes the methane signal especially troubling is that it reverses the expected timeline. In most models, chemical complexity decreases after perihelion as energy input drops. With 3 Atlas, complexity appeared to increase as if new processes were being activated instead of shutting down. This behavior suggests that distance from the sun alone cannot explain what is happening inside the object. The implications are uncomfortable. Methane is often treated as a reliable marker for thermal evolution because its volatility makes it predictable. When that predictability fails, confidence in the entire chemical model weakens. Scientists can describe what they see, but their usual tools struggle to explain why it happens in this order. Importantly, the methane anomaly does not stand alone. It adds weight to the growing pattern of contradictions already seen in size, structure, and chemistry. Each inconsistency might be tolerable by itself, but together they point towards something fundamentally different. The object behaves as if it follows a rule set that only partially overlaps with what we know at this stage. No confirmed natural model explains why methane arrived late and grew stronger as 3 Atlas cooled. Researchers continue to test ideas, but every answer seems to open another gap. This leaves a final and pressing question. If even the most volatile molecules do not behave as expected, what does that say about the forces shaping this object as it moves through space? That question leads directly to the next problem. Because chemistry alone cannot explain how such a massive body also managed to change its motion. Once the true size of 3 Atlas entered the discussion, its strange motion became much harder to explain. For months, scientists had accepted that the object did not follow a perfectly normal path, and part of its movement could not be explained by gravity alone. This behavior is known as non-gravitational acceleration. And in comets, it usually comes from gas escaping the surface as ice turns into vapor. For small objects, this explanation works well. When gas streams away from a light nucleus, it can gently push the object and slowly change its speed or direction. Early models of 3 Atlas relied on this idea because the nucleus was believed to be small enough for outgassing to matter. As long as the object stayed close to 1 kilometer in size, the physics remained reasonable. The new measurements changed everything. A nucleus approaching 3 kilometers in diameter carries far more mass, which makes it much harder to push. In simple terms, a heavy object resists motion changes far more than a light one. To move something this large using gas alone would require an extreme and continuous release of material. That is where the problem appears. Observations do not show the level of violent activity that such a force would demand. The surface does not look torn apart, and the brightness does not match what scientists would expect from massive outgassing. Yet the trajectory still shows a shift that behaves as if the object were much lighter. Researchers explored ways to soften this contradiction. Some suggested that the gas might have been released unevenly, creating a stronger push in one direction. Others considered delayed reactions where heat builds up inside and releases energy later. These ideas help reduce the gap, but they do not remove it. What makes this issue so important is that non-gravitational acceleration is not a small detail. It plays a key role in tracing where 3 Atlas came from and where it is going next. If the cause of that acceleration is misunderstood, then the object's history and future path become uncertain. Every conclusion built on its motion begins to wobble. This does not mean physics is broken. It means the object does not fit cleanly into the category scientists usually rely on. The rules still apply, but the situation may involve conditions that are rare or not well studied. That distinction matters because it shifts the mystery from calculation errors to limits in classification. At this stage, scientists are left with an uncomfortable picture. 3 Atlas moves like a light object, but carries the mass of a heavy one. Both facts are supported by data, yet they refuse to agree. And that tension leads directly to the next question. If motion and mass cannot be reconciled, could the problem extend beyond this single visitor and into how we count interstellar objects at all? Once the discussion moved beyond size, chemistry, and motion, a quieter but deeper problem appeared, and it came from statistics. If 3 Atlas is truly as large as current data suggests, then its detection raises an uncomfortable question about probability. In nature, small objects are far more common than large ones, which means that spotting a massive interstellar body should be rare, especially before we notice many smaller visitors. This pattern holds across the solar system. Tiny asteroids vastly outnumber large ones, and small comets appear far more often than giant nuclei. Based on this logic, astronomers expected that the first confirmed interstellar objects would mostly be small and faint. Instead, after only 2 modest-sized discoveries, a much larger object suddenly entered the picture. One explanation points to observational bias. Large or active objects are easier to detect because they reflect more light or release visible material. If many smaller interstellar bodies pass through silently, without forming bright comas, they could slip past our instruments unnoticed. From this perspective, 3 Atlas may not be typical, but simply easier to see. Yet this answer does not fully resolve the tension. Modern sky surveys now scan wide areas repeatedly with increasing sensitivity. Even if faint objects are missed, scientists would expect at least indirect signs, such as unexplained flashes or unusual trajectories. The near absence of such signals suggests that something in our expectations may be incomplete. Another possibility is that 3 Atlas belongs to a rare category of objects that does not represent the broader population. It could have formed under extreme conditions, making it uncommon, but not impossible. However, this idea introduces a new puzzle. If such rare objects exist, how often do they travel between star systems? And why did one appear so early in our short history of detection? This statistical tension hints at a deeper issue. The models used to estimate interstellar populations rely on assumptions drawn from limited examples. If those assumptions are flawed, then the models themselves may be misleading. 3 Atlas could be revealing a gap between what we expect to see and what is actually out there. At this point, the mystery expands beyond a single object. The real question becomes whether 3E Atlas is an exception or a sign that our view of interstellar space is shaped by what we can detect, not by what truly exists. If detection favors the unusual, then the quiet majority may remain invisible. And that leads to the final question, because once statistics begin to fail, we must ask how much of the universe is still passing by unseen. After everything we have seen, 3E Atlas does not need to be artificial to be deeply unsettling. Its size, chemistry, and motion point in different directions, and together they suggest an object that does not fit cleanly into our current understanding of comets. What makes this discovery powerful is not the answers it gives, but the limits it exposes. As we begin to detect more visitors from beyond our solar system, 3E Atlas may become the reference point that forces science to adapt. So here's the real question. Are we simply meeting rare, cosmic outsiders, or are we finally realizing how incomplete our map of the universe truly is? Share your thoughts and subscribe to keep exploring what we still do not see. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.